Hello everyone, welcome back. In today's lecture, we discuss uh, the eigenvalue problem for the Laplacian. So it's a small digression from our lecture so far. This is also an important and interesting topic, but unfortunately we cannot provide details uh, of this discussion. So this is only a brief discussion, and there are some interesting problems I just want to uh, indicate. Okay, so consider this second order equation. So Laplacian u plus lambda u equal to 0 in omega and u equal to 0 on del omega. So again, as usual, omega is a bounded smooth domain in Rn, smooth boundary. So want smoothness for the use of divergence theorem and other things. Okay, so this can be viewed as an eigenvalue problem for this uh, operator Laplacian, just similar to the eigenvalue problem for a square matrix. Okay, so we'd like to find whether this problem has non-trivial solutions. So u equal to identically 0 is obviously a solution. So we will be looking for non-trivial solutions, and whether they exist for all lambda or not, that we have to examine. Okay. So before getting further, so let's try to see if there are any restrictions on the values of lambda. Okay. Suppose there is a solution which is not identically equal to 0. So you multiply the given equation by u. Okay, that's u Laplacian u plus lambda equal to 0, and you integrate both sides over the domain omega. Okay, so then we get integral over omega u Laplacian u plus lambda, so u into u square, so lambda is just a real number. And then on the first integral of u Laplacian u, so you apply Green's formula, and that will produce minus integral grad u square, and there are no boundary terms as we are assuming u is 0 on the boundary. Okay, so just we get, and that minus integral grad u square, you take the other side, so we get lambda integral u square over omega equal to integral over omega grad u square. And since u is not identically 0, so this coefficient of lambda is a positive number and right hand side is a non-negative number. Okay, so we immediately get lambda has to be non-negative. Okay, so if this given problem has non-zero solution, then lambda ought to be greater than or equal to 0. So if again lambda equal to 0, so just you plug in this previous line, so we get that integral over omega grad u square is 0, and that implies u is a constant, but again since u is 0 on the boundary, so we conclude u identically 0. Okay, and again that is not interesting. Okay, so if we want a non-trivial solution, then the lambda must be positive. Okay, so here we are assuming, so not only this there is a solution, also this integrals are finite and other things. Okay, So just forget about those things for the moment. Just assume all these computations are uh, valid. For example, they are valid if u is continuous up to the boundary and this grad u is also continuous up to the boundary. Okay, so we can assume that there is a solution which is C2 in omega closure. Okay, so next question is, so if lambda is positive, is there a solution? Okay, and is it true for all lambda positive or only certain values of lambda? Okay, so at this juncture we will not be able to answer this question. So we look for some examples. Okay, we'll come back to this problem later. So let's see what happens in certain situations. So we'll, as usual, take a simple case of the domain, namely we take omega to be a ball of radius r centered at the origin. Okay, and then you consider this eigenvalue problem. Laplacian u plus lambda u equal to 0 in B and u equal to 0 on del. Okay, so as a small digression, so let me just explain what is Laplacian in spherical coordinates. Okay, these are useful transformations. Some of you already might know this. Okay, so for example, in n equal to 2 dimension, we use the variables as x and y. So these are x equal to r cos theta and y equal to r sin theta, and the Laplacian in 2 dimension transforms into a second order operator in r and theta. Okay, and is given by this del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square. Okay, so r is positive. So in general, this change of coordinates into polar coordinates or spherical coordinates in general, this transformation is singular at r equal to 0. So whenever we find solutions in this new variables r and theta, we should always make sure that the solution is bounded as r tends to 0. So we'll see as we go along. And in n equal to 3, okay, so just let me mention that also. So here this vector in 3 dimensions x, y, z, I using these as coordinates x, y, z, and this vector r, which is x, y, z, makes the angle theta with the z axis. Okay, and then you project this vector onto the xy plane. Okay, so and that is x sin theta, y sin theta, and in this xy plane you use the polar coordinates. Okay, so that this vector makes angle phi with the x-axis, and then obviously with y-axis it makes related angle. Okay, so the transformation in n equal to 3 is given by x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta. So this r is the length of this vector, that is just x square plus y square plus z square root, and the Laplacian in this case, so this is in rectangular coordinates, del square by del s square plus del s square y by del y square plus del square by del z square is equal to 1 by r square del by del r square del by del r plus, so again there is a radial part, so we call this radial part, and the rest is the angular part. Okay, so this whole thing. So radial part I just write expanded, so this is the usual thing. Okay, so in general for n dimensional case, instead of 2 we get n minus 1. Okay, and similarly you can write in any dimensions. Okay, so there will be n minus 1 angular variables. This is just, so in case there is a possibility that the theta and phi variables might have got interchanged, so you just check that. Okay, so it's just good exercise in differentiation. So express this left hand side operator in terms of this r theta phi. Okay, so with this brief discussion of Laplacian in spherical coordinates, so again let's go back to the eigenvalue problem. Okay, again let me state that. So Laplacian u plus lambda u equal to 0 in the ball and u equal to 0 on the boundary of the ball. Okay, and since this ball is symmetric about the origin and it's invariant under rotations, and same thing is true with the Laplace operator. Okay, it's reasonable to look for a radial solution of the eigenvalue problem. Okay, so we look for a solution u as a function of r only, so independent of the angular coordinates. Okay, so in n dimension then you satisfy this ODE. Okay, so this is an ordinary differential equation, second order. Okay, so d square u by dr square plus n minus 1 by r du by dr plus lambda u equal to 0. So in the study of harmonic functions, this term was not there, so we could integrate this easily, and then we obtained the fundamental solution of the Laplace operator. But in this case there is a lambda, and lambda as we know is positive. Okay, and as I said, we should look for a solution which is bounded as r tends to 0, and in order to satisfy this boundary condition, Dirichlet boundary condition on the boundary, so u of r has to be 0. Okay, and again this a very standard equation, this one. Okay, can be converted into the standard Bessel sequence. And the solution is given by, written here, so a solution of that linear second order equation. So u of r is some constant multiple of this function. So this is jp root lambda r divided by r to the p, and p is equal to n minus 2 by 2, and remember n is there. Okay, so this is Bessel function of order p. So with this knowledge of the Bessel function, we can show that this whole thing jp root lambda r divided by r to the p as r tends to 0 is some finite number. Okay, so it remains bounded. So that's why there will be another solution, because this is second order equation. There will be two independent solutions, but the other one will be unbounded as r tends to 0, and we reject that. Okay, so this is the only solution. Okay, and here I will write down some specific cases. For n equal to 3, so we get p is equal to half. Okay, and j half can be expressed in terms of sine function. Okay, so when we do that, so for n equal to 3, we obtain u of r is equal to sine root lambda r by r. So I omitted that constant, so you can put any constant there. Okay, and you can directly verify. So again, this is bounded as r tends to 0. As r tends to 0, it just tends to root lambda, which is finite. So we can directly verify that this UR satisfies this ODE when n equal to 3. So that means here it is 2 by r. So by direct differentiation, we can do that. Okay, so it remains bounded as r tends to 0. And what about this boundary condition? So we want to have this condition. U of r equal to 0, and that implies this root lambda big R must be a multiple of pi, because those are the roots of the sine function, or this lambda is equal to n square pi square by r square. Okay, so only for these specific values of lambda, so this, at least in the class of radial functions, so we are able to get that. And of course you can still ask what about the non-radial solutions and other things. I will not go into that. Okay, but at least what we have obtained here is, so there is a sequence of positive real numbers, so lambda 1, lambda 2, lambda k, and lambda k tending to infinity. Just look at that. Maybe I should use a different notation here instead of n, because n we are using for the dimension. So let me first. Okay, so this sequence of numbers tending to infinity, so it's unbounded, and for each value of that we obtain an eigen function. Okay, and for n equal to 2, so this p will be 0. Okay, and we obtain this Bessel function of order 0. And Bessel function of order 0 has an infinite number of positive zeros tending to infinity. So again, the same conclusion we obtain for n equal to 3 and n equal to 2. And that is the case for any general n, the only difference being that is given in terms of some Bessel order of some order, and all those Bessel functions, they will have infinite number of positive zeros. Okay, so now come back to the again general problem. Okay, so this, after seeing these two examples, okay, so let's now consider the general problem. So again, a bounded smooth domain with Dirichlet boundary condition. Okay, so let me just state the theorem. Of course, theorem is not very precise, I'm just concentrating on the existence of this eigenvalues. Okay, so there exists again a sequence lambda k of positive real numbers and the sequence uk of corresponding eigenfunctions. Okay, so that means we have just Laplacian uk plus equal to 0 and uk are 0 on the boundary. And further, so there is some regularity. So these UKs are all C infinity function in omega. Okay. So this proof of this theorem is very much non-trivial. Okay, I just would like to impress upon you. So a usual method of proving this theorem is as follows. Okay, first you go to the weak formulation and obtain a weak solution, and then you use regularity results to prove that the solutions are actually C infinity functions. And then in order to get this existence of infinite number of eigenvalues, we need to use theory of compact operators in a Hilbert space. So you can see how technical is the proof. Okay. And this theory of compact operators also tells us one more thing. This is interesting. Okay, the multiplicity. Okay, so there is an underlying Hilbert space here. Multiplicity of each lambda k is finite. So this is an important consequence of this theory of compact operators. What does that mean? So okay, there exists for each k okay, there exists at most a finite number of linearly independent. Okay, so to talk about linear independence, we have to have an underlying vector space. In this case, it is a Hilbert space, linearly independent functions. So let me call that UK1, etc. UK, let me call it some PK. Okay, so that depends on K, such that Laplacian UKJ plus lambda K equal to 0. So this is the one. Okay. So why do we need this? this kind of detailed analysis of the spectral. So this is, by the by, it's called spectral theory, not only just for the Laplacian, in general for a second order uniform elliptic operator. So where is it used? Okay, so let me just briefly explain that. Okay, before coming to that, there is another interesting uh, line one can go. So here again, let me call it spectral function. Okay, so you just define this n lambda is equal. So you just count given any positive real number lambda, you just count the number of eigenvalues less than lambda. Okay, so it's just like counting the prime numbers up to some positive number. Okay, so there is an interesting result regarding this proved by Hermann Weyl. So it was conjectured by the physicist Lorentz. So this is two-dimensional case what Hermann Weyl did, but then it was extended to higher dimensions. So this limit n lambda by lambda as n lambda tends to infinity is, so this one is area of omega. It's a very interesting result, and there are further extension of these results not only for the Laplacian but also for uniformly second order elliptic operators. So you can, there is a old paper by Mark Katz which appeared in 1966, and the title of that is, can one hear the shape of a drum? So it appeared in American Mathematical Monthly. Okay, so you can easily find in Google search. So you will see some history of this spectral function and this Hermann Weyl results and extensions and what is this problem, etc., etc. Okay, so that's an interesting story about this spectral function. Okay, okay, so where do you use this spectral theory? Okay, so consider this evolution equations. Again, I am being quite vague here. In a Banach space or Hilbert space. So you have studied system of first order equations ODE. When it comes to PDE, so we are moving from finite dimension to infinite dimension. So this A is a linear operator. Okay. So in our example, okay, so we have this heat equation, more generally a parabolic equation, and again wave equation. So these can be brought into this form. Okay, and we want to study this okay, this one where to study in some domain, bounded domain or unbounded domain, okay, in Rn and in some time interval. Okay, the standard procedure of proving existence, uniqueness and continuous dependence on solutions. So this Laplacian, so we can replace by second order elliptic operator, maybe with one variable coefficients. Okay. So in general, we will not be able to obtain a solution in explicit form. So we have to prove the existence and uniqueness results by some techniques. Okay, so there are two ways of obtaining such results. One is uh, so-called Galerkin method. So this is essentially separation of variable method. And another one is semi-group theory. So here essentially it is Hill-Yoshida theory, and both these approaches they use approaches make use of the spectral theory. So it's essential to have the spectral knowledge of this operator A in general. So when you consider a general linear operator, that's linear operator, so we have to make use of the spectral theory corresponding to that. Okay, so this is, and with one remark, final remark. Okay, so this so far we have uh, only consider bounded domains. Okay, and the story is very much different if you go for the uh, unbounded domains. Okay, so this I will take up in the next class. Thank you.